So for 6.2, we're going to solve differential equations that have both x's and y's in there. So for this first example, we have y prime equals 2x over y. Just like I was explaining with the slope fields in 6.1, I want you to get your y's with your y primes or your dy's, and I want you to get 2x with the dx. So the first thing I want you to do is to go ahead and write this y prime as dy over dx. I know that's the opposite of what we've been doing. We've enjoyed changing dy over dx to y prime, but we're going to do this so we can go ahead and cross multiply and begin the process of integrating. So when I cross multiply this, I get y dy equals 2x dx. And now I can integrate both sides. And again, I can go ahead and try to get y by itself as much as possible. So I'm going to multiply everything by 2. This is still a constant. Let's call this C1, so I can call this C, because they're technically different numbers, but for our purposes, we don't care what that number is. Even though it's been doubled, it's just a constant. So we're going to leave this like this, and that would be our final answer. We don't need to solve for y here because it's squared and it gets kind of messy, so you're good stopping right here. Okay, so thinking back to Algebra 2 and pre-calculus, when we had direct proportionality and inverse proportionality, looking at growth and decay models, there are always going to be some sort of proportion. The rate of change of y is in some sort of proportion to y. So long story short, once we integrate this once, you're going to be able to do it over and over again, and you will always get the same general solution. So try to follow me through this process, watch it again if you need to, and then try it on your own without looking at my notes, but it's going to be the same every time. Again, I want my y's with my dy's, and I want my t's with my dt's. I don't have a t, but I have some kind of number. I have a constant k. So I'm going to go ahead and write this as dy equals k y dt. I want the y with my dy, so I'm dividing both sides by that. So now I'm ready to begin to integrate this. If I had a t somewhere, it would be on the right side, but I don't. So y's are with y's, my dt is on the other side. You can think of that as dx, it's just a different letter. I'm going to integrate both sides. When I integrate 1 over y, which is what this is 1 over y dy, that's going to give me ln of y, and the other side will give me k t plus c. Again, because k is just a number, so when I integrate that, it'd be like integrating the number 3. It came from 3x. So when I integrate k, it's coming from kt. Now, I want to write this as a growth or decay model, and if you think about what those are my exponential functions. So I'm looking for a way to put this in terms of e to some kind of power. So I'm going to rewrite this. Remember that ln has a base of e, so this is e to this equals that. That just goes back to the log rules. So I'm going to write that as e to the kt plus c is equal to y. I don't need my absolute value on the y anymore because e to any power is always going to give me a positive number. And these are being added, so if you think back to if I had something like x to the 4 plus 5, that is the same thing as x to the 4th times x to the 5th. If you're adding together your exponents there, that means that the bases are being multiplied with those. So I'm going to rewrite this in the same way. This is e to the kt times e to the c. I'm just splitting up that exponent piece. E to the c is just some number. We don't know what our constant is, but it's going to give us some kind of number. So I'm going to change this to just be a big capital C here as some number. E to the kt, multiplying those, is equal to y. And that is my general solution to my direct proportionality change in y over t. This should look like, and it does, all of the exponential functions you've worked with. Think back to when you worked with PERT and how that was continuously compounding and that was a growth function. That is just another way of writing the same thing. The rate is constant, you have some kind of value in the beginning that's constant, and then you're plugging in units of time to get y. And the same thing is happening here. So for the next example, it gives you this again. It says the rate of change of y is proportional to y. What that means is the rate of change of y, so this is as y is changing, it's proportional to y. You have to include the k here because you don't know what kind of proportion it is. Does it double? Does it triple? Does it half? Does it quadruple? You don't know. And so this k value is some kind of number, but we're not sure how it's proportionally related yet. So we have to just leave it as k. As you can see, we're back to the same place we were up here. dy over dt equals ky. That's where I am. So you're going to integrate this the same way. I'm going to run through it again this time, but I'm not going to walk you through it. I'm just going to do it by hand. Once you have that general solution, you're given some information here when t equals 0, y equals 2. 2 equals c e to the k times 0. That's going to be e to the 0, which is 1, which means c equals 2. So I have one of my constants that I need. So I have 2e to the kt. I have another point given to me when t equals 2, y equals 4. So 4 equals 2e to the k times 2. I'm going to divide this 2 on both sides and get 2 equals e to the 2k. And now that I have a variable stuck here, I'm going to rewrite this in terms of ln. So this is ln of 2 equals 2k. Again, I'm saying e to the 2k equals 2, so I'm just rewriting it and dividing both sides by 2. You get k equals ln of 2 divided by 2. Now I have a specific equation, and I can say that my equation is y equals 2e to the ln of 2 over 2 times t. This specific solution will allow me to plug in any other point. And let's see, it asks for the value of y when t equals 3. So I'm going to plug in 3 invert t right here, multiply it times ln of 2 over 2, e to that power of whatever that is, multiply it times 2 and get some answer for y. I don't have a calculator handy, but the answer is on the answer key for these notes. Okay, so all of these are going to be based off of the same principle with growth or decay. So we now at this point can assume and know that we're working with the general equation y equals c e to the kt. Note that if you're on an assessment and I ask you to prove the rate of change of y proportional to y gives you this formula, you'll have to walk through it just like we did in the other example where you're actually starting from here and integrating both sides. So you'll have to show how this lands you here. So please make sure you can do that process. Okay, so for this one, we're going to start with our master formula here, y equals c e to the kt. And then this, all that's happening here is just some Algebra 2 pre-calculus stuff. We're finding a formula based on some information. So suppose that 10 grams of the plutonium isotope was released in the nuclear accident. How long will it take for 10 grams to decay to 1 gram? The half-life is 24,100 years. So we are starting with a value of 10 grams. We're asking if that much is released, and then it decreases to this, which means that when t equals 0, I'm getting that c value of 10. And I'm looking for when it's going to be 1. So it's 1 gram at the end, that's my final amount. It started at 10, and I have E to the k times t. So what you have to ask yourself now is how this half-life is going to contribute to this equation, because we're still missing two variables. We need to know how much time it took t, but we don't have the value of k. So if we don't have k, we're stuck. So I'm going to go back to this principle here that the half-life of plutonium is 24,100 years, and that's going to give me my k value. What that means is, for example, I could use 10 again if I wanted to. For it to get halfway down, so if it started at 10 and got to 5, it's been cut in half. I have a t value for this one. My half-life is 24,100 years. It took that long for this to become this, so I have a t that I can plug in. I'm going to divide by 10 here as well. Whatever two numbers you pick, since it's halving, you should end up with 0.5, because that's half. Equals e to the k times, it took 24,100 years for it to get down to half as much as it used to be. When you take the ln of both sides and rearrange this, you end up getting that k equals ln of 0.5 divided by 24,100, which is negative 0.000028761. But now I have this value and I can plug this into the formula where I was actually trying to find how long it took to decrease to 1 gram. So I'm going to say it's 1 gram, it started out at 10 grams, this is e to the negative 0.1234, 28761 times t. Divide both sides here by 10, I'm getting 0.1 equals e to all of this. I'm going to again rewrite this in terms of a natural log. When I rearrange that, I get ln of 0.1 equals negative 0.000287661 t. I divide both sides by that. And then when I do that, I get that it took approximately 80,059 years. So as you can see, none of this was actually calculus. All of this was going back to plugging in for growth and decay. You just had to know that if you were told only this, that this is leading you to conclude this general equation, which then allows you to walk through all of this. These next two examples you should be able to walk through by yourself, especially with the answer key. You're following the same exact process as the one we just did. So you need to be starting with this formula. You need to find the values of C and K, and then figure out what else it's asking you to do. Is it asking you for another value? Is it asking you for the equation? What is the point of the question? And I would try both of these and then look at the answer key and compare how you did to the answer key's work.